Welcome back, everyone. We now begin lecture 1 to be delivered by our esteemed foreign faculty, Dr. Professor Sukumar Kamla Sadan, sir. Sir, we are eager to learn from your vast experience. Please, sir.
Okay, can you hear me over there? Okay, so good morning, everyone. So, what we have done, how we have planned this course is like you see in the title, the course is Modeling and Management of Inverter-Based Resources Integrated Electric Grid. So, there are two parts there, as you can see from the title. One is inverter-based resources, and the second one is integrated electric grid. Integrated electric grid sounds like inverter-based resources integrated or electric grid integrated, because in the electric grid we have normally talks about electric grid transmission system and electric grid distribution system. You may be aware of that, right? The electric grid is kind of, if you look at it, can be divided into parts, transmission network and distribution network. So electric grid is one part, and then IBR, okay, and then connected together. So I was just mentioning to professors, the IBR, when we talk about inverter-based resources, there are parts in the IBR. One main part that in the inverter-based resources that we electric grid interact is inverter. So if you look at inverter-based resources, there is a source, then there is some power electronics devices, then come the electric grid. So if you say inverter-based resources, it consists of source and then power electronics and grid. And power electronics part, that as a electric grid person is more interested is a power electronic device called inverter. That's why it is called inverter-based resources, right? So power electronics, so you may ask the question, oh, okay, so is there any other things in power electronics? Yes, you have other devices in power electronics, which you can call as a rectifier or some other ways. Basically, what it does is changing from one form of, source side where it is DC, in the case of inverter, to AC, right? So that's why the word inverter-based resources, because as a power grid person, you kind of don't care about other parts other than inverter, because inverter is the one which is connecting the power electronic side to the electric grid. So that's why this name came into being. So you may be wondering why. So it's generally called inverter-based resources because inverter is the one which is the key connecting the power electronics, or rather connecting the DC side sources to this. So if you talk about this, then this meaning this course especially, we are focusing on modeling and management, right? Modeling and management of electric grid with inverter-based resources, right? So like I said at the beginning, how we planned this course is we will start today to talk about electric grid first, and then we talk about electric grid, how the electric grid needs to be modeled or changed from conventional modeling to include inverter-based resources. So that's the first part. So we'll talk about that today. We'll talk about how we do that from the electric grid side. So we will not, we will conveniently say how you need to represent inverters for electric grid modeling, and very in a light form, basically how the electric grid sees when the inverter functions. And then slowly we will start looking into the details of modeling of inverters as well when they progress, maybe the second day, third day, and depending upon that. So with that, are you following what I'm saying? Okay. So with that, and just to give this pulse on the audience, how many are are doing undergraduate program, undergraduate studies, UG, UG. Okay. And in this UG group, have you taken one course in power system? How many have taken one course? Okay. And how many have taken no course in power system? No idea about at all power system. I don't know nothing about power system. How many? You should write no. This is not all required for me to understand. Three. Okay. How many have taken at least one course in power electronics, like inverters? Okay. How many have taken no course in power electronics? No idea about power electronics. 2, 3. So for the group here, I think 3 or 4 who don't know about power systems and power electronics, whatever I'm talking about, suppose it's not it's too much for you, please raise hands and ask the questions. To make this move forward, I may have to tell you, we'll talk about later, but that's okay, just because of time. And then I will in offline talk to you about how to enrich your experience. Otherwise, you will be too out of context, right? So that's the reason. How many in the master's program? Masters. Okay. Yeah, any masters, power system, all are power system masters. Anybody in all are power system. Okay. How many in any master students in power electronics or power systems? I'm asking this because I will have to talk about power electronics. So I have to. So all the students in the master's program, you have taken one course in power electronics. Some basic idea about power electronics. If no, and raise hands. If yes. Okay. PhD scholars, how many? And you have, power systems and power electronics, I guess, basics. And then I will try to enrich your experience. Faculty members, I'll try to enrich your experience. Maybe I'll learn from you, but I'll try to enrich as much as I can and just try to connect some spark, some things which you will enjoy. Oh, I see. I'd love to something like that, but beyond maybe. So that's the kind of. So we will talk about mainly power system today, basics of power system in this part, first part, and then I'll talk about a little bit about how do you model the power system on what we call it as steady state condition. Do you know what a steady state means? Steady state means normal operating condition. Like you are in a car, you are we tell in the US called cruise mode, meaning you press the button, you are like no problem, nothing is happening, roads are good and no stop, and so that we call it steady state. Steady state meaning you do not expect any changes. Okay, in the steady state, unfortunately, electric grid, there is nothing called steady state for electric grid because every time the load that is connected to the electric grid is changing. So the generation of the electric grid changes. So such changes in general we call it ambient condition. Ambient means normal ambient condition. Okay? So those changes in the electric grid sense, for an electric grid, we see like a noise. Everybody know noise, right? Noise is something which is not good. For electric grid, it is good. The change in the load is some small changes. Okay. So those small changes, what happens? Why we call it noise? Because that's not very big. So you still go with the same change load generation, balance. That load generation balance condition is called steady state. Okay. So first time when you model an electric grid, there are two words there: model and management. Okay. When you model an electric grid, first model for an electric grid is to make the model of the electric grid perform during steady state. Okay? You cannot model anything if you cannot model steady state. Right? So that model of electric grid is required to understand how the electric grid runs in steady state. Okay? So you may ask the question, I don't know whether you are aware of this or not. Why do you model anything? Oh, models are basically mostly on electric grid originally, and it starts with mathematical models. Okay? Is there any other kind of models other than mathematical models? Yes? No? Oh yeah. What do you mean by physical model? How do you get a physical model? It's existing. Okay. So why you call physical model? That's the physical system. Because it's the same. Why you call it model? So the model means that it is a representation of the real life. That's why it's a model. So if anything that you physically develop or design is not a real, but a representation of the real is called model. So for example, if you develop if you want to see a 1 MVA, I'll still go back to some interesting power electron. I'll still start going. So it's an inverter. It's a 1 megawatt inverter, 1 MVA inverter standing there, real life, physical inverter. But can you represent the inverter using a 1 kW system, physical? That's called model. But representing means what? Representing the characteristics of the real device is what the model does. So there are physical models. You're right, spot on. Physical models are, So now you may call that, is it really a model or is it a prototype? So you may hear people, professors telling you, okay, make a prototype in the lab. What is the difference between prototype and a model? Do you know? I don't want to digress the talk, but I just wanted to see you some. They are different. But anyway, so I'll talk about what's the difference in sometimes when you talk, while you work on it. So the models are actually representation of physical model. Any other models? Hmm? What is product? That's scale down model. Okay, exactly. Yeah. So we'll talk about what are the difference in prototypes. Okay. Yeah. Since that broad area, prototypes are scale down models means what? Either representing the characteristics fully of the real system, but it's still not at the reach the level of models that you can call that as a real system. But they are whatever scale, you call it lab scale or, different levels of scalability, right? Some are not scalable. So what happens if you have a model or a prototype sitting here, which is not scalable? Is that a good representation of a physical system? No, right, because it's not scalable. You're not right. So what is important there, since you brought that up, it's important also to understand the model that represents the physical system, right? At the end of the day, the characteristics of the physical system, it also should be scalable. Okay? So idea of modeling is actually not just developing something. So how do you know that it represents the characteristics of the physical system? How do you know the model is scalable? There are some specific checks. First check is you look at a physical system, you run a operational test on a physical system, you put an input, you get output, you can collect the input output information. It can be input output characteristics or input characteristics, whatever you want to do in the physical system, collect that data. Then you go to your model, you run the same, and then you compare, match, see whether it's operating same as well. That's one. So if you develop a model, it has to represent the characteristics of the real physical system. If you develop the model, it has to be scalable. If you develop the model, you have to run some tests or experiments on the model to make sure that it is doing the checks and balance. And one test is characteristics of the real system with respect to the model. What is the second test for scalability? What do you do? Well, you got to perform test with respect to the scale of that model. So if it's a device, what is the scalability test? You interpolate that model to perform on a higher power capacity, for example, or a higher voltage level capacity, and then you do a test to see whether it's scalable. What do you do with a power system model? Our system is system, right? Models are, there is another modeling difference. One is a model of a physical device, another is a model of a system. Modeling of the system is a little bit different. Modeling of the system has models of physical devices inside the system. So like 7 physical devices in the system, if you want to model a system, you have to model all the 7 physical devices, right? And then you bring up the model of the system. So how do you know the scalability of the model of the system? By performing the test on the model of the physical for models of that physical system and increase the number of parameters or variables on the physical system. So in a power grid, scalability is tested by testing these models running on number of points on the power grid. Number of points on the power grid is generally called as nodes, okay, or buses. Okay, what's the difference between a node and a bus? I think you are actively participating. Other people on power system. What's the difference between a node and a bus? If you do, it's not even power system. If you do an electric circuit analysis, you do something called nodal analysis. Have you heard of nodal analysis? Okay. What is a nodal analysis? What is a node? Two or more number of points that is connected on its two physical device that you have. If you have a physical device, you always call this has got a physical device can be represented as a two-port network, which means input and output. So this device, another device connected together, that point is called node. Good. So you node voltage analysis. You take this node and then you do analysis. Analysis of what? Voltage. Node voltage analysis. What do you analyze? Voltage. Voltage of the nodes. How do you analyze voltage of nodes? It's a different story. We'll talk about later. So it's node voltage, node analysis, right? Node. What's the difference between node and a bus? More or less? What's the difference between a node and a bus? PhD scholar, you're back. You know this all. What's it? Huh? Classes are? Yeah. Collection of nodes meaning suppose there are 3 nodes. All the 3 nodes collected together will become a bus. Actually, it is yes. But that nodes has to be at the same point. Can I have one node in one point, another node in another point, connect them together and call a bus?
Yes.
You cannot. So let's have a bus, right? One node connected to the bus, another node connected to the bus, third node connected to the same bus. Then it is a bus, collection of 3 nodes. One node here, another node here. That's not bus. There are 2 buses, different buses. So buses are one or more number of nodes at the same point is called the buses. Okay. How well will that happen? It will only happen if you have 3 connecting points or 2 connecting points or 1 connecting points coming together. Okay. In an electric grid is operated in what we call it 3 phases or 3 connecting lines. Okay. So if these 3 connected to one point, there will be 3 nodes made by these 3 lines. And that 3 node we call it as a bus. Can the 2 lines connected to one point is also called as a bus? Yes, it is also called as a bus. It's a 2 node bus. Can one line connected to one point, which is a node, can it be called as a bus? Yes, it is a bus. It's a node and the bus. But generally, you call it node. You don't call it separately as a bus. So you see the difference between node and the bus. So the node and the bus will only happen in electric grid because you have more than two lines or three lines connected, right? But this is generally represented for a three connected nodes in electric transmission system or a bulk electric grid. There will be three lines connected together. On a power distribution network coming to your home, sometimes you will have one node, right? One phase or two phase, two nodes, right? So such things are called nodes. I'm saying this because you will hear in what we talk today, model of electric grid, buses and nodes coming. So nodes, you can say, representative for electric distribution system. You will have two nodes, one node, things like that. In the electric transmission system, we call it as buses. Are you all following? That making sense? What I'm Yes. Okay. So electric power system, when you talk about, you connect these devices together to form a system and you represent the scalability of the model. That's what the story we were. Okay, scalability of the model by testing these parameters on a scaled system, which is represented by buses or nodes. So an electric grid is a representation of electric grid. How many nodes in your electric grid? Electric power engineer talk about that. So that kind of spark to socialize. Say, how did you test it? Did you test it on how many nodes? That's actually to test the scalability. Oh, I tested it on 3,000 nodes. Oh, wow, that's good. The model is now very good. Is there an end to it? There is no end to it. I can test it on 30,000 nodes. Characterization says that if at a good level of node testing which you do or bus testing you do, it can scale up to higher level of nodes or higher level of bus so that you can run it on a real system. I don't know the numbers in India. I have not gotten myself educated with it, but in the eastern side of the United States has got 30,000 buses. That is one section of the United States. So if you want to really implement your models on a real system and do some test on projects coming from DST or so large scale project and showcase to the country that, well, I built a model and that's real. I can test it on real. You may want to scale it up to that level and test it. So what we learned so far? We learned about models. We learned about the difference. Why do you want to do models? We learned about what type of models you do first in an electric grid, steady state condition. We learned about the models that you do in electric grid consist of devices, and the device models on the electric grid, collection of them together, you represent that on the electric grid modeling. Testing the model, you test it quickly writing. These are not in the slides, by the way. So if you want to write it down, you may want to. I'm just still trying to set it up. So when I show you on the slides, you will know why this is coming. Otherwise you'll say, stuff we did. I don't care. I don't know what is going on. So we don't want that. That's why I'm setting this up. So you have models, which is, devices connected. These models are representative of the real system. There are other type of models called physical models. Is there any other type of models other than physical model? I just want to say that too because it'll come at some point of time. There are models which are not really representation of physical model. So for example, suppose you want to find a model of a real system, but this model is not possible to make mathematical model. Okay, is there a situation in which you cannot make a mathematical model of a real system? Or everything can be done through mathematics? System complexity becomes very high. If you have a system that is very complex, okay, you cannot necessarily make a model. How do you assess the complexity? What do you mean by complexity? How do you assess the complexity? Complex systems are not dependent on the resources are actually inputs or things on the system, right? Complexity of the system means the system behaves in different ways at different times or different conditions. Okay. So if to capture all those behavior into one representation, it's hard for you to develop such techniques or such bases. So for example, I'll give you one simple example of what we call it as nonlinearity. So if you look at a device, a very small device, diode for that matter, any nonlinear device, not the linear device. Some devices we model represent as a linear device. So if you look at a diode for that matter, it has got nonlinear. You know what a nonlinearity means? What's a nonlinear characteristics of behavior means? If you apply an input to the system, when you look at the output of the system, for example, input output, nonlinearity, the output is not linear to the input. If the output is linear to the input, you can represent the linear model in the form of mathematical model using linear equations. The output is not representative of the input. What do? You have to represent nonlinear equations, right? For representing a nonlinear equations, it's not that easy. What happens if this device operates in different characteristics in different region and you want to capture all of it? Well, then you are having the mathematical complexity increases. What happens if this device behavior changes with respect to conditions? When the weather pattern changes, the behavior of change. So then you say, oh, that's uncertain. It's not very certain what this. So you have to represent uncertainty of the device. You have to represent some ways to find out which point the system operates in an uncertain behavior. All these things are nuances or changes that you have to make on the modeling side to represent a system which operates in different ways. So you, or device. So you can say, oh, it's a very complex device to model. That's device complexity, not the input number of inputs increase or number of output. Do you have a complexity in the number of inputs and number of? Yes, you do can actually have 7 input that has to go into this device to model a device. 25 input that goes into the model. Again, that's a different level of complexity. I'm talking about device complexity. So complexity in general, you can call that whatever that level which you have. So the modeling is actually dependent upon that, and mathematical models are related to mathematical tools that we get. And we are not mathematicians. As an engineer, what you do? You borrow the tools that is developed by mathematicians and try to sneak in and get and do some art to make this model of electric grid work on that. You don't originally develop. There are some mathematical sciences you develop looking at the physical system, but that's what you do in general, right? That's mathematical. So what happens if you cannot do mathematical model at all? Then you utilize model development based on operation of the a real device, looking at the data. So you put an input to the device, some bunch of data, you record the data, and then you look at the output coming from the device, you record the data, and then you do an input-output mapping. That mapping can be done through, for example, an Excel spreadsheet, and you put a regression equation for the represent non-linearity or anything on the device. Such models are called data-driven models. You can also call that as a some gray box. There are, I don't know whether you know the difference between white box model, gray box model. Again, that's a weak talk. We'll talk about that at some point of time. But generally, they are data-driven. Okay. There is also something called data-induced. And there's a difference between those two. Shown and induced both are not the same. So that's why I'm saying that in this course, which I wanted to bring in all these nuances, so smaller changes, which otherwise you don't know what you're doing, in general. Anyway, so you understood the models, right? These are different type of models. Having said that, now probably we can pick up the pace and you will understand what we are talking here. So today main job is basically to bring you an essence on what? How do you model a system or a device? How do you model an electric grid system? Number one. Number two, how do you model the electric grid in steady state condition, operating condition? And how do you, on that very light or rather modeling part on IBR side, and sprinkle or tell you how to model a very baseline representation of IBR. And when you do a baseline representation IBR, we'll talk about baseline representation just inverter. how to model that. So that's our goal. Good. Many of you, I will start from the fundamentals. So once I start, from fundamentals, you can hear me with this, right? I'll speak up a little bit. This will induce more noise, which is will not be ambient, and will be tough for us today. So, in the modeling, what we will focus on is just the electric grid model. Many of these electric grid model you may know. If you don't know, you have you may want to if you don't know, you may want to raise hands and stop me. Then I will tell you what will be the difference in modeling of electric grid when you consider inverter based resources. Am I going too fast? How many of you think I'm going too fast? Is it? Am I going too slow? Good. You understand what I'm talking? Good. All right. So, yes. So I just wanted to get some honor to research students, which help me build different aspects, which I'm talking here. Three of my research scholars. Um, so the motivation of this modeling is all related to one specific thing about inverter-based resources. Okay? Inverter-based resources are coming to the electric grid. Why it is coming to the electric grid? Why inverter-based resources are there in the electric? Anybody? You don't know? It's there, so I'm happy and I'm doing something right. Do you know why they are there? So it's actually related to renewable energy integration. Renewable energy integration in the electric grid is because of two reasons. What number one? Huh? Environmental aspects in renewable energy based inclusion reduces, for example, carbon emission because they are not fossil fuel based. That's one. What's the second one? Yeah. So it's actually also to do that. So these two are the main part, renewable energy. So as a power engineer, you really don't care much about inverter or inverter based resources. However, then why do you want to, if you are worried about renewables, why you want to talk about inverter based resources? Because most or the two mature renewable based technology that is connected to electric grid comes on connected to electric through inverters. One is photovoltaics. Everybody know PVs, photovoltaics. It actually generates the power in DC, and then you have to connect it through inverter. Second mature renewable technology, mature wind. So when I was a wind, then that's why I was just wind connected to the inverter. Not necessarily, but wind is connected to the electric grid through back-to-back inverters. AC, DC, DC to AC. Why you use inverter? Why cannot you connect the wind directly to the electric grid? Because of the wind speed is not constant or synchronous. But since it is not constant or synchronous, you have to make it to a constant speed, which can be done through this magic device called inverters or power electronic device. Why they are magical? Because they take that speed and convert that into frequency and then work with all this magic frequency and bring another good frequency at the end. And that's constant. So that's why in the wind farms or wind to mature technology uses inverter. So it's basically inverter based. Okay, so this is good. So because of that, future power grid are expected to increase a large number of inverter based resources. Okay. Inverter based resources comes in two forms. Inverter based resources is connected in a one specific location on electric transmission network that we call it centralized, meaning at one location you have inverter based resources. Very minimum such resources are very minimum in the electric grid so far, because it requires a vast area of land to have an inverter-based resources at that scale to develop. Okay, so much of the inverter-based resources are also spread out in different areas. Okay? Such inverter-based resources which are spread out, or non-inverter-based resources which are spread out, are called distributed energy resources. Okay? So you will invariably see people talking about DER, IDR, all these acronym. I don't know what's going on. That's because it's a distributed. So these distributed energy resources must be from inverter, not necessary. You can have a distributed energy resources which are non-inverter based. Okay, what's an example of a non-inverter based distributed energy resource? Any small hydros are non-inverter based distributed energies. How about diesel generator? Diesel generator, which is running on a diesel, is you can take that box and put it anywhere. It's non-inverter. So you got it. When why I'm asking these questions, as far as anybody, any learner for that matter, especially when you are a deep learner called researcher or a light learner for called hobbyist, everybody needs to think about why and what. Do not worry about how I do this or what software I run. So I'm just trying to do my best to ask this question. So DER, that's the difference between distributed energy resources. There is also the term that you will see called RER. RER are renewable energy resources. Okay, renewable energy resources. Can the renewable energy resources without an inverter? So you may ask the question, RER. I thought that's IBR. So why do you want that? You have a renewable energy resource without inverter. Same hydro. It's renewable. Hydro energy resources are renewables. Hydro resources are renewable. So that's renewable. If that's a central renewable, not distributed, you call it RER, right? I mean, you can call it central or distributed. RER is a general term. Renewable. How about nuclear? Some people say nuclear energy resources are renewables. And nuclear is actually renewable, except for the waste related challenge that's associated with renewables. And there are renewables that is now coming up, especially in the US, maybe in India too. They call it small nuclear reactor or SNR. Small nuclear reactor means nuclear reactor in a small scale, which can be connected into any areas. So there are people who are trying to develop small nuclear reactors. Okay, so how do you how do you how do you so we talked about models of electric grid, models of the electric grid in steady state. Are you writing down, right? Models of the electric grid in steady state. What will you do with the model of the electric grid in steady state? What will you do with the models of electric grid in steady state? Okay, models of a device in steady state. What will you do? You use it for what? You use it for checking the operational characteristics of the device. We remember that we mentioned. So you must say, what operational characteristics I will check if it is steady state? You check what? One operational characteristic that you can check for a device. Huh? Power rating or capacity. Is this something, for example, inverter? Okay, 1 MVA inverter. If I give 1 MVA or other power that is drawn from the inverter is 1 MVA, will it really work or will it collapse? That's what you call it, capacity test for rating the capacity, which is normally done there in the undergraduate lab. We call 3 different type of tests that you perform in a first energy conversion or machines course. What are the 3 tests that you do? Have you heard of no load test? Have you heard of no load test? Yes. Okay. What do you do in a no load test? You take a device, do not connect any load to the device, and you run the device. Why do you do a no load test? What will happen if no load is connected? You just check the no load losses on the device. You also check another thing on no load test. What is that? Huh? You look at the voltage, output voltage of operation. You cannot check the current flowing through the device in a no load test. Can you? No. So if you cannot check the current flowing through a no load test, how can you check the losses in the no load test? There are some part in the device which is consuming the current, which is not going out. That part of the device which is consuming the current will generate some losses, and you are checking that loss. So no load test losses or no load losses that you talk about are the device or the parts in the device which is connected in parallel or connected in parallel branch is also called shunt, connected in shunt form. Okay, that's what the no load test is. Any other test which you do on the then you do what you call it as full load test. Have you heard of full load? There you check what? First you check the voltage, you make sure voltage is correct, then you check the current flowing through this and see whether the current can flow through that. What do you check? What do you check in that? You check the thermal characteristics, ability of the device to perform very well when the current is flowing through the device in full load condition. So you can change the loads step by step and go to full load. Then what will test you do? What's the third test? Short circuit test. This is fundamental. This is UG. Everybody should be saying this. This is the thing. If you do any course in the third year, I guess, whatever the year, we have it in this, there, at least by third year, you should be doing this. So it's called short circuit test. What do you do in short circuit test? You apply a short circuit on the test, on the device. You apply the short circuit on a rated voltage, right? No, you cannot apply any short circuit on the, if you apply a short circuit on rated voltage, everything is go off. You will also go off, maybe with the machine or device. You apply a short circuit test on a rated current. You try to increase the voltage slowly up so that the current on the device increases up to the rated current. So voltage will be small. These are the kind of story that we do in a lab, it's undergrad. But anyway, so on the steady state condition, you do what? Capacity test. Okay. Capacity test in general in the electric grid is called power flow. If you want to do capacity test, especially on the full load test, you have to have the power flowing through the device. Okay. So the power flow is basically what you do on the capacity test. So that in general on electric grid is called power flow studies. Okay, that's the study that you do. Everybody heard of power flow studies? Yes. Okay. Power flow study is also known as load flow test or load flow studies. Okay, so interchangeably called load flow or power flow. Why you call load flow? You are giving a load so the power can flow. Otherwise, your load. So you may ask a question: what load will you give? Well, you can give anything. Nobody tells you that you should give one load. Necessarily, very importantly, you will give one specific load, which is the maximum load that can be connected to the device or the system to test the performance capability of the system on what we call it as full load. Remember full load test, right? That is not necessary that every time you get full load. Why do you give a full load on a power grid and do a power flow study? What happens when the load is connected to an electric grid with the power flows? Why do you want to do full load test? When the load is connected, what happens? Load current will be drawn from the source to the load. On an electric system level study, when the current is drawn from the source to the load, if the load is not connected directly to the source, the load is connected in some other node or some other bus. Now you should connect with all I'm talking about. So some other bus, what happens to the power flow? Power has to flow all the way to that bus and go to the load. When power flows to a conductor or a wire, what happens? Losses happens, and when the losses happen, what happens to the voltage? Voltage on each of those nodes or the places that is flowing through started collapsing. It's actually like a water in a pipeline. So the water is full in a pipeline, you get a good pressure and go all the way up. The pipe is clogged, what happens? Nothing comes out. What happens if the pipe is full clogged? Not only nothing comes out, water start hitting on the side of the pipe. It may burst the pipe and it starts seeping out. Okay? This is what you call it as energy imbalance, or energy is coming in, is not going out. Because of the energy imbalance, it will affect the one point and then it bursts. Similar thing happened. So what are we doing now? In the steady state condition for a model of an electric grid, we do what we call it as load flow studies or power flow. Are you connecting my? I'm connecting with the storyboard. Not losing the train of thought, so that you should also go with me along with that. So what we do is load flow studies. So basically, efficient load flow methods can solve power system with DER, distributed energy resource. So when you solve a load flow study in a power grid, you may also want to talk about how the power grid is organized. Everybody know the organization of the power grid in two different layers. One is called the three layer for that matter. One is called generators on electric grid, located at different points, connected to conductors and wires, going through a specific system called transmission system. And after the transmission system ends, it comes into a location called stations, and they are called three different names. One is called receiving station, where you receive the power, bulk power, or it's also called substations. There are stations which are many of them connected, and that substation that drives that power to the loads, which are called distribution network, which is connected to the loads called industrial loads, residential loads, and we have loads that is connected from inverter-based resources called wind farms, battery energy storage, solar farms. All these are inverter-based resources. So see the number of inverter-based resources are loads. Inverter slash loads. So some consume power, some deliver the power. So all these folks are connected right there on electric distribution system. Here you model the electric grid in one phase representation of three phase, and such models are called bus models, where buses are considered as three nodes connected to one point, and you run the model in one phase representation. Okay. Ideally, electric transmission systems are not run in phase based model. It's running connecting all three phase to one line representation, and those models are generally called positive sequence representation. How many of you heard of this word, positive sequence? How many of you heard of the word positive sequence? No, nobody heard of positive sequence? No, nobody. The sequence of generations. There is supply the sequences. There should be a negative sequence. There are these and some positive negative combination of all of these why do you think of the sequence? Representation actually is a representation of a system to see what is the effect when there are connected devices in that system on each phase separately. What is the challenge of connecting a device in the system in each phase which are not same? Then the current flowing through each phase will be different. Current flowing through each phase will be different at this point. What happens to the voltage on each phase on this point? Will be different. Why? The drop will be different. Forgetting about other things, drop will be different. When voltage is here on this point and current is different on this point, what happens to the voltage and current? And then you do not have such things, or what we call it as unbalanced nature of an electric grid. Unbalance contributed by changes on the load on each phase. So you may ask a question, can unbalance contributed by something else? Yes, imbalance can be contributed by many factors. One factor is changes of loads in the system. But another thing is unbalance. What are the another part that contributes unbalance? Huh? Huh? Yeah, that's a good thing. So when we started, what models are we doing? Steady state. What do you mean by steady state models? Is that a normal operating condition or abnormal operating condition? Normal. So one thing in electric grid is a very important thing that you mentioned. One thing electric grid, whatever you do in electric grid, you want to define your scope. If you start looking at everything, they're all different. So we are not talking about abnormal operating conditions of electric grid, we're doing normal operating. When you apply a fault to the electric grid, is that going to be a normal operating condition or an apply? No. So having said that, let's park that discussion of unbalance created by fault so that we talk about when fault is applied to the electric grid. So in the context of electric grid being normal operating condition or its steady state condition, what else causes unbalance? Okay, you have three lines, right? Three lines, right? Remember, three lines make one bus, or three lines, three. Each of these lines is transferring power from point A to point 3, and current changes from point A to point B, and the current changes from point A to point B will create electromagnetic waves that is changing from point A to point B. When that changes from point A to point B, what happens? These conductors can affect the voltage at each point because of these changes in electromagnetic waves. That point goes from point A to point B. Okay? Such conductor related changes affecting the current because of the inductance in the conductor and resistance affecting the current can also create unbalances on the voltages. That will only happen when the current flows. Without the current flow, these folks are just great. They will not do anything. Current starts flowing, they will behave differently. So they will create unbalances on the system, right? It is predominantly going to happen if you have the conductor which are not laid or which has three phase, two phase, and single phase. So one way to take care of these unbalances, we call that you change the conductor orientation at different points, and then transmission grid we call it transposition or transpose. Okay, that's the concept of transpose. So people may ask, why do you transpose? This is the reason you transpose. When you transpose, what happens? Your system are going to be staying balanced. Two things which you do, you transpose, and you also make sure that the load connected to each phase are same or close to same. You cannot make it same because it's hard for you because you don't know who all are switching the power, and then taking the power, right? So these two things are the main reason. So when will it happen? In which type of electric connections it will happen more? In the power distribution network, there the load aggregated values are going to be different in each phase, and there will be two phase, three phase, one phase connection, and then it's hard to transpose the lines too. So most of these, because of that, we say electric distribution system is unbalanced in nature. Electric transmission system is not balanced. That's because of the nature that we are representing in the system. So if you wanted to run an electric distribution model, you have to take care of the unbalanced nature. And if you are doing in an electric distribution system modeling to take care of unbalanced nature, you need symmetrical components, or you need positive sequence, negative sequence, and zero frequency reference. So how do you represent that in transmission system? Do you care about positive and negative and zero sequence? Normal operating condition? Do you care about that? No, you don't care about that. So how do you represent the electric transmission system? Well, you take one phase power, multiply it by 3, whatever the total, represent that as like a one line, and then you run the models in electric. Good. So, so you are just basically talking about this, and you also need to develop models in two other forms, which will come later. One is when the system is not in steady state, when the system is changing, not abnormal, changing. That type of study or analysis is called dynamic study or dynamic analysis. Okay, when will that analysis happen? It will happen when the load that is connected to the system is not just a noise, it is going up and down. Okay, so you treat that by changing the load in the form of what we call steps. Okay, when you change the load in the form of steps, you will see the generation will also change. So you see dynamics. Okay, not in cruise control. When the speed goes very low and you accelerate or decelerate, you see this, that is called dynamics. Okay, so you have to do dynamic study for representing. Oh, if you do a dynamic study, what type of models do you need? Dynamic study will change the power flow with respect to time. Dynamics, it changes the power flow with respect to time because the changing the load. So such model should be time dependent models. What is a general classical time dependent model representation? Time dependent model representation in mathematics, you utilize a tool called differential equations or differential equation based models. Oh, so can you just run the models in differential equation using a differential equation of electric grid? You also need to run some of the devices which is not changing when the dynamics happens. How do you run the models? You run the models in algebraic equation form, right? Algebraic. Oh, by the way, I missed the little bit of connection. I'm just trying to storyboard as much as I can. Then I think I can quickly move because of this wide variety of all the models in the power flow you run through with respect to time or no time. Huh? Steady state models you run through no time. Okay, so they are called algebraic models. Algebraic model means that it is not nonlinear. No, algebraic models can be nonlinear. They are two different things. Nonlinear and non-nonlinear. Algebraic and different, they are two different things. We're following this story, right? So algebraic models you have. So some of the devices in the system are dynamic, some of these are not dynamic. So how do you combine together? So electric grid is then represented as or so-called differential algebraic equations or DAE. You will see this term, people talking about differential algebraic equation, differential algebraic, right? Some people also call this ADE, algebraic differential equation. I just flip it because you don't know whether algebra comes first or differential equation comes first because it's combined at close to form. That is the one which you do when you run a dynamic model. What happens if you are going to have a condition where something happens to the electric grid? Means a tree fall on the power line. Such condition when it happens on the electric grid, we call it the electric grid is operating not normal. Okay, so such things are classified as abnormal operation of electric grid. What happens if it is an abnormal operation of electric grid? You study the electric grid for abnormal conditions. One abnormal condition that you applied to study the electric grid is connecting one phase on a power line to the other phase on the power line, and you call that as fault analysis or fault conditions. Oh, can you connect one phase to the power line to other two phases on the power line? Yes, you can. This is also called fault analysis. What happens if one phase on the power line connected to the ground on the ground? Yes, it is also called fault. There are 7 different varieties of fault analysis that you can perform on electric grid. And the hardest one, we call it all the phases connected to the ground, and that's called 3-phase bolted fault. And the fault on the power line can also be on line. Can the fault connect on the bus? You know node and bus now. You cannot say no, you don't know node and bus. Can the fault happen on the bus? Yes. Will the fault happen on the bus is worse than fault happens on the line? Yes. Why? Because all the devices are connected to the bus. Devices are not hanging from the line. Lines are just in the conductor that going from point A to point B. So because devices are connected on the ground, everything is affected very bad, and all the interconnections happens on specifically on the bus. So we call it three-phase voltage bus fault. Lot of words, but that is what the bad fault. So you study what we call a fault analysis. It's also called short circuit analysis, short circuit study analysis. Why? Why fault analysis is fault based on the real? Why it's called short circuit study, short circuit analysis? Because that affects the capability of the devices to supply the current towards this fault, and that affects what we call as momentary supply of current towards a fault, and it is tested using our short circuit study. Remember the short circuit study which we did? That's why we call. So short circuit study is for what? For the device. Fault analysis is for the what? For the system. But you interchangeably utilize because you really don't care about what you do. You just need to only worry about what happens on the system. But they are two different things, by the way. You just don't mention that. You say, okay, short circuit study. It's a study that you perform because your study is done on a device, what happens to each individual device. Analysis, fault, use on the system. You analyze the system, what happens on the system. So you see, always you call it fault analysis. You don't call fault study. I'm saying all these things because there are a lot of things, especially on learners and researchers, many things that it seems that they don't really clearly see the difference. So we call it fault analysis. We learners say fault study, but you say short circuit study. Study is for a device. You are understanding the performance of the device or a parts in the system, how it works. Analysis is for basically to understand on the system what happens on the building. This is giving you a few things. Hope you are understanding what I'm talking over there. It's good. Okay. So so that's basically right. Now what? So let's look at the inverter out from the equation. Don't worry about the inverter. Okay, it's just an electric grid. Why do I want to model an electric grid uh, without an inverter differently, hoping that inverter will come? My point is, let's assume that inverter is not in the electric grid. You're not modeling inverter as a device in electric grid, and you have an electric grid. Okay, an electric grid modeling, power flow study, you're already doing classically for how many years now? 120, 130 years or something. When the machine started, Stanley and these folks in 19 some like that. So, having said that, power flow studies have been done before, right? What is the new in power flow study when IBR comes in place? Without modeling an IBR, is there anything different? If there is nothing different, then I can say, hey, the only change is IBR coming. Let's model the IBR, connect it to the device, and then go for, right? Yes, there is one big difference. One big difference is that the power flow study, when you study on an electric grid, you study the power flow and transmission systems and distribution systems separately. And distribution system, you probably don't do a power flow study because you connect all the distribution load lumped on an electric transmission network and connect to electric transmission network bus as what we call it as a spot load. Spot load meaning one load. What's the difference between varying load and spot load? Is the number in the load changes, it's become non-spot? No, spot is on location, varying is on number. Right? Spot loads are loads that is connected to one location. So when the buses change at different buses, you have different spot load. Do you have a buses without any load connected? Yes. You have electric grid with a buses without any load connected. So all the loads no need to connect it in all the buses. You connect all the loads in different buses and you represent this load and these buses as aggregated one load. Okay. What happens on the bus? Is that load connected on the bus on transmission network? No. The whole distribution system is connected on that transmission network. Do you care about distribution network? No. We just say spot load, one load. How do you represent that load on the transmission network? You represent the load as active power and reactive power, and you represent the load as S. S as in Sam. S is what? Apparent power. You represent the load as an apparent power, which is active and reactive power, and you put that number, one number, for the entire electric distribution. Is that good? Entire electric distribution, you put it one number. Yes, that's what we have been doing for 170 years. Will that work? Yes. Believe it or not, it works. And it works to run the power flow on transmission system. Okay. How about the distribution network? Yes, don't care about power flow. You do a small way of representing the power flow on a distribution network to calculate the losses so that you want to know the voltage. So in the distribution network, the focus is to maintain the voltage profile throughout. The transmission network is focused on getting the power and connected as a spot load. Are you following? Is it getting complicated? You understand what I'm saying so far? Okay. So that's what you do. Transmission network power flow. Sometimes there is a distribution network power flow. You connect it with one substation and then connect it to distribution network. So do you need to think differently now when the IBR comes in place? Yes, you need to think differently. Why? Because the IBR, when it comes in place, there are few things that happens. Number one, these IBRs are connected on distribution system. It's spread out, and that is called DER, distributed energy resource. They are connected on this. What happens if they are connected on this? All the current flowing through these transformer and all the way right here, they are going to change. If these IBRs are pushing power to the electric grid, for example, electric vehicles, at some point of time, or taking power from the electric grid, so these loads are now coming to become what? Generators or load. If it is consuming power, it is called consumer. And if it is whoever is consuming power is called consumer, that is for probably market. If it is delivering power, it is called prosumer. Delivering power is called generator. And then if you consumer and prosumer both done in different time, consumer and generation both done in different time, it is called prosumer. There's a new producer and consumer basically. That's the word people talk about in general when you go to the big group called prosumers. So there are folks who can act as a prosumer in this case. What happens if there is a rooftop solar panel on our building and it is supplying the power to the electric grid? What happens to that? It produces. What happens if this is consuming power at some point of time as a load? It is called consumer. So this whole thing becomes two main difference. One difference is it's not acting as a generator, it's also it's not acting as a load, it's also acting as a generator. Number one. Number two, there are multiple of such generators and load connected in different points. So you can, the concept of treating them as a spot load at some point and putting that power at point and running the power flow will no longer work because these folks are seeing. What happens in the transmission network? Well, you still have distributed resource on transmission network. So you may not have to look at that way, and you may have to look at differently. So such modeling has to be done not just power flow models on transmission network, but power flow models of transmission and distribution network together, and that is called integrated transmission distribution network and thank you, integrated transmission distribution network modeling, and it is also called integrated electric grid modeling. So when we look at the title of our GAN course, IBR integrated electric grid modeling, it can be IBR integrated or it can be electric grid integrated because you have transmission systems and distribution. You see now, so that integrated word is a integration of studies on electric grids or integration of IBR on electric grids. There are two different type of part that we are trying to study. So today our goal is actually by end of the day today, hopefully to talk about electric grid, not conveniently bringing IBR in the picture model wise, and also not talking about dynamics or fault conditions, electric grid modeling in steady state, because we learned so far that we have a job to do. What is the job that we have to do? To develop power flow models of the electric grid connecting transmission and the distribution network. So having said that, how many minutes we have now? 30 minutes maybe? Hmm? Half an hour. Well, there can be conditions in which you have load on your house and you have solar farms. So when Well, I want to also look at the concept of electric grid when you have prosumer connected. Prosumer, everybody know the word now, right? Prosumer. When the prosumer is connected, how do you model an electric grid load? It should be spot load, right? Now that spot load is not going to be spot load. So how do you model an electric grid when you look at from electric grid standpoint? Whether it is prosumer or consumer or whatever it does over there, I don't care what you do. I need to model. How do I model? I call that load as net load. Okay, what is a net load means? You're taking some power or you're giving me some power. Difference of those two power, I call it a net load. When I run the net load on one specific condition, is it net load changing with respect to time? Is the power from sunlight delivered to the electric grid? Assuming these homes are connected to electric grid, finding it. I think you know net metering and everything, like the PV farms connected to electric grid, delivering power to electric grid, then you get some money. When the PV farms are connected to the electric grid, you don't turn on the electric grid and you lose some money, right? So this is the net load, which means generation minus load. What happens if the generation is less than the load? It is net load. If the generation is greater than the load, it is net power coming from the generator, right? So if you are at a home and if you are having a rooftop PV and you are consuming taking power from rooftop, still you have a load connected. So you consider this as net load and you model that as a net load and you still is a load. So when the load is higher than the generation, it's considered as load. When the load is lower than generation, it will be a generator. And that's what your question is, right? There is nothing to do with the PV. Photovoltaics are still going to generate power, whatever it is, because of the load connected on electric grid. So having said that, I hope you got this whole story here. So this is an electric grid with a current transmission and distribution system model. This is a transmission system. This is the distribution system. What will you have to do now? Okay. Now I'll speak less and then ask you to engage more. So you understand what is happening on the slide. So the random, so will this model affect the randomness of the photovoltaics? Right? So do I have to run the spot load in different conditions? You should engage, okay? You should understand whatever you understood, you should take it. And then you should engage. Okay. Spot load has to be changing different. Yes, you need to, right? That's a different thing. That's called randomness, right? So the randomness transmission distribution system connected together is called co-simulation. Combined simulations models of transmission and distribution system. Okay. All right. So now we will start looking at some basics. Is this story known to you? Can you read the slide and then say whether that makes sense to you? Transmission system, power producer has generating station, prime movers, transformer, transmission company, this distribution utility. Simple, right? Baseline. Okay. High voltage network, medium voltage network, loads. How do you manage the electric grid? You manage the electric grid in a control center, right? There are two levels of control center. One is called load dispatch center. I think it's called in here, which is basically dispatching the load based on whatever the load. What is dispatching means? What is dispatchability means? That's a big word, another big word. What is dispatching? Dispatchability means? What is dispatch?
Dispatchability probably has to do with ability to ignore the rest as per the
Dispatchability is spot on. Dispatchability means you ask me 5 megawatt, I'll give you 5 megawatt. You change, sorry, 7. Yeah, I'll give you 7. Say, no, not 7, 3. I'll give you 3. You ask me 250,000, I'll say, no, my capacity is too much. I'm too low, I cannot give you 2. Until my capacity, I will not bother you what you ask, I will give it to you. Okay, such resources are called dispatchable resources. To do that, you need two things. You need to have sources that can give that power. You also need what? You need a control system to change that source to give the power in combinatorial time, we call it, which means in a good time. Don't give the power tomorrow, give it sometime in near future, and we call that as dispatch centers where it is controlling those power to go to the, okay? All the conventional generating resources are called dispatchable. How about renewables, inverter based resources? They are generally called non-dispatch. You ask for 5 megawatt and I say, no, I don't have a sunlight. I'll give you Zoom. That's called non-dispatch. Can you make a non-dispatchable source dispatchable? You could, by some ways. That is what we call it as people are working on. So, for example, I connect a battery to this source, and I have a lot of money, and I connect a big size battery. Store all the power in here and ready. Trust me, three. I'll give you. Trust me, such called dispatchable. Oh, do you need a control system for that? Yes. So takeaways, you got to write it down. There are some things. One is the power requirement from the generating source. What is another requirement? Control system to do that job, to give the power. Okay? So people are working on dispatchability or dispatchable nature of IBR, how to make the IBR dispatchable. Or do I need to consider the dynamics of inverters? Yes, I need to consider who do you control when I want to make this dispatchable? Inverter, so do I need to know the control system of inverter? Yes. Is that going to be different from generator? Yes. So how do I need to control? Nice story. Everything you can do and do a 4 or 5 dissertation or thesis out of it, and then you can do research. And so I'm just giving you the context. So you know your scope in here, which is control system that is required. So system analysis and practical power system is done through this path, and for that you need to model of the system. Jumping onto models of the system, this is how you model a generator. If everybody is good, I will move forward fast. How do you model a generator? You model a generator as a source and a connecting inductance, because generator as an inductance, a generator generates a source, never EMF. Okay, so such models are generally represented in the form of two forms from electric circuits. All these models are background is electric circuit. I forgot to ask you how many of you got a first course on electric circuit. I hope you have done AC circuit analysis, which is important. Oh, is that DC circuit not important? Yes, it is important because of inverter, but that's not that important for electric system level study. So, what type of model that you are talking about for generating sources? We do that in two forms. What is called Thevenin model. Another is Norton representation. Thevenin models are generally called in the power electronics world, and I'll tell you some analogy while I go through. In the power electronics, we call it as voltage source models. Okay, voltage source representation or voltage source model. Okay, is that voltage source same as voltage control? No, they are not same as voltage control. Voltage control means what you are controlling. Controlling is voltage. That's voltage control. So power system folks says that Thevenin model, power electronics source is voltage source model. And that what's the difference between a Thevenin model and a voltage source model? There is a difference. Voltage source model is a model of that source directly at the source point. Thevenin model is a source representation not just on the source point, it may be somewhere else on the point. Still I represent as a source. Why do I do that as Thevenin model? Because in electric grid, if you wanted to reduce the size of the electric grid, some part of the electric grid I need to ignore. So another part of the grid I stand here, I say, bring the source here, and then I call this as a Thevenin model, and I do that for. That's the difference. That's why we do Thevenin model. I don't know whether you're catching. I'm going a little faster now because I also have a content delivery time. So I hope it's okay, and I think somebody, whoever catches, can translate it also. So Thevenin model representation is done by voltage source connected in series with the impedance, generally called Thevenin impedance. But for a synchronous generator, it's not represented as Thevenin impedance. It is called inductance. Thevenin inductance. There is no resistance. Why? Generating sources in generators are necessarily represented as inductance. And this inductance is called synchronous reactance. In general, it's also called X sub S, synchronous reactance. X represents the reactance and L represents the inductance. What's the difference between the inductance and reactance? The fundamental frequency reactance is equal to 2 pi F L. So L is the inductance and the reactance. And why do you worry about fundamental frequency? Why did I say fundamental frequency? Which is 60 Hertz, obviously 2 pi F is. What happens if it is non-fundamental frequency? It is not going to be same reactance. It will be different reactance. Why do I say fundamental frequency? Because in steady state operating condition, we are running in fundamental fluid. What happens if it's a fault? Well, then it's going to be non-fundamental reactants. How do you represent a non-fundamental reactance of a synchronous generator? You call it XD prime. I don't know whether you heard of this term. We call it transient reactance. Now, what happens if the time will become so fast and the reactance value changes non-fundamental? Yes, then it's called XD double prime. We call it. I don't know whether you know these stories or not. That is a transition from the fundamental one moving on to XD double prime. So the representation of that in the form of X sub S. What's the next D? You're coming back again to what we call it as transformation from real to virtual. Real systems are A, B, and C, three phase. If you represent a three phase of a synchronous generator, you have to represent everything in three phase. And we call that, oh, these three phases are balanced. Why do I need to spend a lot of time representing three phase? So you bring the three phase into two phase representation and model. Magically, you can do that with the help of somebody named Park and Clark, who did a Park transformation and Clark transformation. None of the things is done by you. You are sleeping, you borrow what they did, and then you say that is transformed to ABC to DQ. Going through alpha beta, ABC to alpha beta, then go to DQ. How do you go to ABC to alpha beta and then to DQ? Story you can look at your books and then say. So you get what we call it as DQ. And that X sub S now will become X sub D because you care less about Q. The D is represented as active power related. XQ is represented as reactive power related. Why do you don't care about reactive power here? Why you don't care about voltage and reactive power here? Because you are doing steady state modeling and you're doing power flow. What power flow you're working on? What power? Active power. You're not working on reactive power. So, anything else in here? Okay. So, the represented is E. What's the difference between E and V? E is generally called EMF. V is generally called voltage on the bus. So, can E be V? Most likely no, because it goes through a EMF connected to inductor connected to V. Can V be E? No, because again it is connected to the source. Alright, so maybe there are other small things here. I may not have time, but pay attention to the details in here. This is how we model a transformer. Transformer models are known to you. Two winding transformer equivalent circuit model known to you. Yes, everybody knows about this. I don't think there is no brain here, and you represent it in the form of referring to primary, referring to secondary. All these are fundamentals. And at the end of the day, you neglect this. Oh, this is what it happens to circulate no load current, and we call it no load losses. This will not only for full load test. You do not short circuit test, all the story. Now, if you neglect this, what happens to the transformer? Another series impedance. Generator is an impedance. The transformer is an impedance. What happens to the transmission lines? Again, an impedance connected. Okay? Loads. Loads are generally considered as the constant power loads connected to a point, and that's called spot load. There are two different variances of the load in real system. Real system loads are not generally. Do you know zip loads? Constant power, constant current, constant impedance. No? How many of you know zip load? Raise your hands. One. Loads connected to the electric grid. If I ask for 5 megawatt load, if I take 5 megawatt all the time, it's called constant power. Constantly taking 5 megawatt. So you may ask a question, will it take less megawatt? Yes, it takes less megawatt depending upon what voltage level you have. Taking 5 megawatt or electric bulb says that I'll take 60 watts, when? 230, right? Whatever voltage is there. Not 120, 220. So it takes 60 watts from 220 volt. What happens if the 220 volt become 120? Have you seen an electric incandescent lamp? Forget about these ones. The one bulb. What happens to this bulb when you apply 120 instead of 220? It will be same as your candle, whatever it says on the reading, right? You know that or you know that? So it is not taking that power. It is taking less power when the voltage changes. So they are not considered constant power. It has to take constant power all the time, right? So the loads are not necessarily constant power. So you may think, oh, then that means there are some loads which are changing with voltage. Yes, there are some loads which are changing with voltage. Such loads which are changing with the voltage can be categorized into two forms. One is constant impedance and constant current. Okay? What happens if the constant current? It keeps the current constant. When the voltage goes, power also will change depending upon that, keeping the current constant. What happens if the constant impedance? And when voltage changes, it keeps the current also changing to make the impedance constant. We call constant impedance. So there are three types of classifications of the load in the real life. How do you know that this is constant power and this is constant? I think you should do an undergraduate project. There is nothing like constant power and constant current. Then loads that is connected is a mix of constant current, constant power. So you want to represent the load in the form of a model to look at the system. Okay? I'll tell you that model later. Now I'll go a little bit more detail about the electric distribution system. You understand the modeling of electric transmission system. This is fundamental. No renewable energy idea. Electric distribution system starts from a point where the electric substation is connected. If you do an electric distribution system study, what will you do in this point where the substation is connected? You represent that point as a voltage source. Connect a voltage source at that point. Okay. What happens behind the substation where the power is coming from the transmission system? What will you do? Just neglect it and connect there as a voltage source. So what's the property of the voltage source? You know, right? No, you don't know. What's the property of the voltage source? It will give you, no matter whatever current is pulled by this voltage source, it will give you, you say that the voltage at that point is stable. This voltage at that point is not changing. Okay? So if you have a voltage source, and if this voltage source ideally is connected to another line and behind the scene, if I represent this as a voltage source, do I need to model anything behind the voltage source? You don't have. So you can cut there, say my life starts from there. So distribution network is modeling the substation as a voltage source. What happens to the voltage on the substation? Will it be constant? Then only you can represent as a voltage source. Remember? Yes, it will be constant. Who will do that? Somebody else will do that. I don't care about that, and I will do as a voltage source. So this is how you. So if you have anything to be modeled, if you cannot consider that as a voltage source, please don't consider it as a voltage source. That's what I'm saying. So it's important to know what you are trying to do in your modeling world. So voltage source connected to what? In the beginning of life in electric distribution system, it goes to a transformer first. And that transformer is generally known as LTC. Not the same name, I guess. It's OLTC. OLTC is LTC is a short form, and OLTC you can call it as long. What is OLTC? On load tap changer. Have you heard of this? What is on load tap changers? Changer means it changes the tap of a transformer. Do you know the tapping transformers? You know what a tap of a transformer means? I only target you, undergrad. No worry about other. Do you know what a tap changer transformer means? How the transformer works? You know, transformer changes the output voltage based on the input voltage, and that is done through stepping. It's called stepping up or stepping down. What is a tap changing transformer means? What is a non-tap changing transformer means? It step up and step down only one voltage. 220 volt, 12.47 kV. If I ask, can I get 7.47 kV? It will say, no. I am designed for stepping up 12 point. What's the tap transformer means? Tap means up to 12.47, I can tap and then get any other voltage in between. Called tap transformer. I'm just very baseline saying, otherwise there is a knowledge gap. So tap transformer is used to what? Tap the voltage, change the voltage. Why do I need to change the voltage? When the current flowing on the line, distribution line changes, is that current flowing on the distribution line in your control as a utility or as a generator? No. Who will change the current flowing on a distribution line? The houses, the loads. People like, I need light and I change the current. When the current changes on the distribution line, what happens to the voltage? Voltage goes up and down. Why? Because of the drop on the distribution line. This is fundamental. So when voltage goes up and down, who will have to maintain? Oh, do I have to maintain that voltage? He said constant voltage, right? Who will maintain the voltage? Utility has to maintain the voltage. If the voltage is going down, utility will shift the voltage up. Utility will change. So there is a device in the electric distribution system which does the job at on the substation side, and the name of the device is OLTC. It will look at the load and then change the voltage. That's why it's called load tap changer. If that is done online without somebody going there, changes. Done online, it is called on-load tap changer. Oh, is there an off-load? Yes, there is an off-load tap changer too. But it's done. These are something in general control theory wise in electric distribution system, we call it tertiary control. Tertiary control means it's going to take some time. Can this happen in every second? It happens in 5 minutes, 15 minutes, 20 minutes. There it happens in 15 minutes interval, or one time in a day, or one time in 3 months. This is what generally happens. So it actually changes with the load connector. Following, right? So how is the voltage changed? Dependent upon voltage or current? Depend on current. Said load tap changer. Oh, so you may ask the question, oh, is there anything else which changes based on voltage? Yes, there is somebody else. One thing is there in India, that's why I gather from ISC. That's somebody else who changes the voltage based on voltage. So if you keep a transformer, and I look at my, well, do you know in a transformer something called load side and source side? Source side is a source connected to the load side is a load that's going in. If I have a transformer, I look at the load side and there is something voltage changing on the load side. I change my voltage on the source side. Such transformers are also tap transformer, but they are operating based on voltage on the source side, changing the voltage on the load side, changing the voltage on the source side. Why do I need that? If I do that, if I yeah, it is not required, but I'll go back again. So if you look at a distribution network, we have a long line connected distribution network. There are buses in here. Distribution networks are generally considered as like a tree formation. This is how a distribution network looks like. Okay, this is like a tree. You see a tree? How many of you see a tree in my drawing? It's a tree. This tree has a main trunk here, and there are branches. Okay, in the distribution network, these branches are generally called laterals. Laterals means branches. Okay, this trunk is always going to be mostly three phase. Okay, we have three trunk which is going out. These laterals can be two phase or three phase depending upon the connection point, and from here it can be one phase or something like that portion here. This is how you represent a distribution network in general. So will you see unbalance on the distribution network? Yes or no? Why? No. Lines are 3, 2, and 1. Oh, how many unbalance you can have? Yes, load is that also important. How many unbalance you can have? Two type of unbalance we talked about. Remember, one unbalance is because of change in the load, single phase, three phase, two phase. What is the other type of unbalance? Lines, bringing unbalance. It can be. Can you have both in distribution network? Load unbalance and line unbalance? Yes, you can have both in them. It's a different story. I'm digressing a little bit, but I'm just connecting with this what we discussed. So this is a distribution network. Okay. What happens for the voltage in a distribution network? If you plot the voltage on a distribution network, starting from substation, looking at these buses points, depending upon the distance, you will see the voltage on the distribution network mostly something like this, which means that you have 1 per unit here. You may have 0.95 per unit at the last point. This is with respect to distance, and these are node numbers. I'm plotting the voltage at every node. Okay, node numbers organized in the form of the distance, not necessarily node number starting from the substation. Why am I saying that distance again? This one point right here, this distance is more. I'll be putting this distance and up to this node, then I'll start from this node because that distance. Okay. So when you have like that, this is the voltage. If it goes from 1 to 0.95 at this point, you're good. I'm happy. Everything is taken care of. What happens if this one goes like this, 0.92? I have a problem. The loads connected from this point to this point, they will see under voltage. When you see under voltage, the loads which are connected, lights will not turn on. We talk about incandescent. So there is a need for me to boost this. That is right. Can I also change this line? This line like this. So I shift this entire line. Okay. So if I shift this entire line, how do I erase it? But if I shift this line, let me say I'll do this differently. I got it. So I'm moving this line now. Up. If I move this line up from here to here, will it work? Yeah, it works. What happens to this voltage? Well, I have to make sure that this voltage will not go beyond 1.05. Right? You understand per unit? Everybody understand per unit? 0.95, 1.0. Okay. So if I can lift this and I bring this to 0.97, everything is good. Who does that? This is done with the help of LTC. So what is LTC doing? LTC is looking at the load and then shifting this up. What happens? I shifted this up and this voltage become 1.1. I will shift this down. Let's say this is 0.92. And I shift this down 5 points below to 1.05. When I shift this down 5 points below, 0.97 will become 0.92. So I have a problem. I cannot shift it up, I cannot shift it down. What will I do? You see the problem or you don't see the? How many of you see the problem? If I shift it up, it's hit more than 1. If I shift it down, it's going below 1.95. Can that happen? Yes. People are not looking at it. I could see what's what. Do you see? Okay, what will you do? Oh, I have another trick. I'm going to keep it right here and I'm going to boost. I'm going to redraw this. 0.95, 1.05. It's bad news, right? At this point. So I will do something to move this up and then do this. Again, my drawing is not that great, but move it. Can I do that? So I go from here to this point, then I shifted this voltage up, then as long as I shift it between the band here and then bring it here, I'm good. Are you seeing this? To do that, what do I need? I need somebody here sitting and shifting this up. That job may be suppose here. Who will do that job? This is done by somebody called voltage regulator. What's the difference between voltage regulator and LTC? Voltage regulator will look at the voltage and regulate the voltage. What voltage? Voltage at the load end of a transformer. Regulate the source end of the transformer. What happens to the LTC? It looks at the load and changes the. So this voltage regulator is a device also used to regulate the voltage on electric distribution system. So yeah, so you represent that in the bus variable mode, and then it'll take 5 minutes more. Is that one?
Point with this connection. Between the difference between the voltage regulator and the DC cannot be very clear. We put it. Ultimately, both are doing
the same thing. Both are tap changing. One is changing the tap based on the load side voltage and changing the tap on the source side to improve the load side voltage. Another is changing the tap looking at the current on the distribution line and changing the tap to improve the voltage to change the tap. Again, load side. But one is looking at the current, another is looking at the voltage. Okay? Yeah, it's just the control method is basically what is doing the trick. And the essence is the same. So do the current and change the voltage. What will the controller do? Controller is doing the I times Z, changing the I times Z to change the voltage and change the tap. The other one is doing the voltage on the transformer on the load side and then changing the. So the one who does the voltage and changing the voltage is called voltage regulator. On the distribution side is called distribution voltage regulator, DVR, distribution voltage regulator, not distributed, distribution voltage regulator. And the one who does on the changing the current and then looking at the current and changing the voltage is called load tap changer, looking at the load. And so you may ask, there is a little bit story behind it. I haven't completed the whole story, which was not the whole point. So you may ask the question, yeah, looking at the current and changing the tap of the voltage, right? It was beyond the time, but
Sir, can we go for voltage upliftment by using the FACTS controllers?
yes.
Yes.
So that is a good story that segue to few things. Can I control? So this is a load tap change. I mean, this is the voltage regulator doing the job, right? Voltage regulator doing the job, right? What happens if I connect an inverter there? Can I change the voltage using an inverter? Yes, you can. Not necessarily change the voltage, but you can change the reactive power coming out from the inverter. If you change the reactive power coming out of the inverter, will the voltage change? Yes, voltage can change. So can I use an inverter to change the voltage instead of a tap changer? I mean, instead of a voltage regulator? Yes. Will that be beneficial? Yes. So we there is a project we implemented in the field. We said that some regulators are not even required if you have a inverter connected at that. So we call it in our thing called asset release, meaning you invest 2 million. So one regulator is generally costing 800,000 US dollar. I mean, just a general number. I don't know the number here. But that regulator, you can take it out. put it somewhere else. That's called asset release. So you compensate for the investment. So you have a big inverter sitting there, the inverter money is kind of offsetted because of that. So there are many things. So can a fact device you can put it to regulate the world? Yes, you can. Is that fact device putting there is an overkill? If you have an inverter connected at that point, overkill means, is that really required? Is the inverter connected and you also get photovoltaics coming out? Maybe that's the best option. But the bottom line is that voltages needs to be controlled. Now, these voltages are generally controlled in every 15 minutes. This is normally done in 70 seconds, something like that, the time frame. This is 1 minute, 1.5 minutes. So anybody who can do that job in less than 70 seconds, can you control? What I mean, if there is a device just does the job 75 minutes, I cannot use because this is running. So time frame is important. It's done by all control systems, done by the controllers working on the device, not necessarily functionality of the device. Controllers on different devices work differently. Fastest one are power electronics based devices, which you can perform very fast and get the controller done. Is that too fast is a problem? Yes, too fast is also a problem. So how do you regulate to make it, so these are all what we call it devil in details kind of thing. A lot of things needs to be assessed carefully. But is that a good thing to do a study? Yes. So just to say some juice for thought for this. Yes. So fact devices can also so everything can be modeled. So how do you model a line? How do you model a load? This is a load model. This is a zip load model. Zip load is actually represented as a constant current and constant impedance. This coefficient on the top you can change to give you a combination. You can change to square, which will give you voltage square, basically the power representation. You can change to 1.05. That means it's a mix of constant power and constant current type of. So these are all classical meaning. This is in the books. This is in the literature or whatever you call it. So it's nothing new. I'm not bringing something, but since it is a course, I'm talking about the old what has been done. So this is a zip representation. This is a constant power, constant current, constant impedance. This is a representation of a voltage regulator input and output. So you can control both based on Vj controlled based on Vi. Vi is generally called that I is generally represented as input voltage and that J is represented as an output. And A is what we call it as tap ratio. I don't know whether you've heard of this term. Tap ratio. How do you model a tap ratio? What is a tap ratio? What is it?
Percentage of the
Voltage output divided by voltage input nominal is basically what we call as a tap ratio. Tap ratio is number of turns on the secondary, number of turns on the primary divided by number of turns on the secondary. N1 divided by N2 is V1 divided by V2 is called as A. This is third year, second year. So I think you should also know, but that's what the tap ratio is. So we have that. And this is how we model a capacitor, and you can also model an inverter. This is a first inverter model representation. Very simple. What is that inverter doing? Inverter is looking at the rated power and subtracting that with the power flowing from through the inverter. Why do you subtract the power flowing through the inverter? Because that's the requirement for the photovoltaic. I will say that, hey, I need to get 5 MVA or whatever. Subtract the 5 megawatt. You subtract the power flowing to the inverter. Then find out how much reactive power is left in the inverter based on the capacity. And you use that reactive power to what? To regulate the voltage. Such inverters are called smart inverters. Many inverters do not have that capability. Do not have the capability means what? Is this reactive power? Oh, it's a story, another story. Where is this reactive power coming from the inverter? Is that because of the inductance? Oh, can the reactive power comes based on inductance? Can you get a reactive power based on inductance winding? Yes? Yes, okay. Can you get the reactive power based on a capacitor? How do you get reactive power from the inverter? Do you have an inductance inside the inverter? Inverter, not the filter. No. Do you have an capacitance inside the inverter? No. How do you get the reactive power? Reactive power of the inverter is free. It's coming without any cost associated. How do you get it?
Change the phase of the current.
It is actually that we get it by the difference between the angle of the current and the voltage flowing through the waveforms inside the inverter. Oh, by the way, there's a fundamental difference in analyzing something inside the box, which is power electronics, and something on the electric grid. Electric grid, you analyze everything in most of the time in phasor representation, which means you represent in RMS quantity, phasor, and angle. Inside the inverter, when you go there, it's another world. You will see always waveforms. You will always see waveform. There is nothing which we call it as phasor. You always talk about, so the RMS value is not existent inside the inverter. You only talk about peak. You don't care about RMS because you don't worry about RMS. Angle, no. Only sine omega t plus theta or sine omega t. Everything is represented in the form of waveform. But because it represents the form of waveform, there is a phase of that waveform changes, you get reactive power. That's how you get reactive power. So it's a different way of control. Why? Because Q that is coming out is Vi sine da da da. What happens in the electric grid? Q that is coming out is V square divided by Z minus U. So you got a Z or the X, which comes Z, by the way. We call it Z, and I changed my style Z, V divided V square. So equation is different, analysis is different. Just to give you. Okay, so power flow model, I don't think we'll have a lot of time, but we'll wrap it up and then we will come back, and in the afternoon we'll talk more about it. But I will just talk about the power flow. If you want to do, so in the afternoon session, we'll just go on power flow. We talk about power flow of a distribution network, power flow of transmission network, and integrated power flow of a distribution transmission network. I will just give you a segue on how do you do a power flow. Power flow is done using these three main equations. That's it. Okay. So you take a bus. You say that the power going into the bus is the same as power going out from the bus. This is something coming from very famous fundamental called KCL, or Kirchhoff's current law. Current going in is the same as current going out. Which equation represent here? Current going is equal to current going out. Which equation represent that? This equation right here represents the power balance equation. What happens in the power balance equation? The power coming in, it is the same as the power going out. You can represent DR, load, everything on the power balance equation. What is the second equation that you see in a power flow? Second equation is voltage equation or voltage drop equation. We talk about the voltage on this bus related to voltage on another bus. How these voltages are related? Voltages are related based on voltage drop and reactive power drop. So this is basically the voltage balance equation or voltage drop equation that happens on the electric grid. One more fundamental equation which is coming out in all these things, you represent them in complex form or in apparent power form, which is S, which is represented as VI conjugate. Conjugate is another story. Why conjugate came there and all the story, probably you know that. So when we come back, we will do the power flow study or first. Master break.
Sir, thank you very much for enlightening us with the modeling aspects of the inverter-based resources, and you have started the discussion with very fundamental part, and I hope that we all have learned a lot with this session. So, thanks a lot, sir, for this particular session. Again, we will meet after the break, sharp at 2:45 p.m. here only. All right, so everybody is requested to proceed for their lunch and then again reassemble at 2:45 p.m. sharp. Thank you very much.